Okay, so we're gonna get started. In terms of announcements, your next quiz is up. It's very short, only a couple of questions, but get started on it anyway. Your midterm should be out very soon. It's basically the Chapter 1 and Chapter 2 quizzes all over again, so don't expect too much different. We'll hopefully have quiz 3 out next week, which will be about the assembly stuff, and then you'll probably have like one more quiz and the final project, which basically be like a review of everything we've done in class. I expect today and especially tomorrow to be a lot less attendance in office hours. So if there's something you've been wanting to ask that you think is supposed to take a while, be a great time to come would be probably today and tomorrow because not that many homework assignments are due. But we're gonna pick up from where we left off. But before we do you guys have any questions? Yeah.
Is the final going to be like midterm or like a homework assignment?
The final is going to be like a midterm. It's going to be like a series of questions that you answer because cannot think of like a good because most of the stuff that we cover after assembly, it's not really like testable with a program, so I don't do a program.
Okay, and then we're gonna have like 2 more homework assignments.
Yeah. Anything else? So again, what were our 3 rules? The 3 rules for the GCC C calling conventions. The return value should be placed in the AX. Right? So there are 3 things that we had to deal with. How do we pass parameters? How do we return values? And who's responsible for saving what registers? So the values are passed on the stack, right? And you push them in reverse order of appearance. So if you had ABC, you'd push CBA. And then the final thing has to do with who's responsible for saving what registers. The caller saves which ones? EAX, ECX, and EDX. And the called register or the called function is responsible for all of the other ones, right? So those are the 3 rules that we have to obey. That makes your code callable from C. If you want to call C functions in your code, you also obey those 3 rules, right? Last time we left off, we had finished doing this line where we allocated space for our array using for C, right? At least for the rows of C. But now we have to go through and do the for loops. Yeah. Right? So we did this line right here. And now we have to go do this line over here. Right? Which you guys have probably done quite a bit already. So how do we do this? Sure. So over here we might say I will be, or what's going to be I? What register? Which one?
ECX.
Sure, ECX, that's fine, right? So over here, how do we start the translation? If I is ECX, 2% ECX, right? This is I equals 0. Then we have outer for start, right? Outer for end. Right, which is equivalent to I minus numRows less than 0, and its negation is I minus numRows greater than or equal to 0. Right, so how do we do this part? So numRows, right, remember, is 4 words past EBP. Right, this is what our stack look like. So here's currently where EBP is at because we did the prologue. So we have 1, 2, 3, 4 to get numRows, 4 elements past EBP. So we can either compare it directly with the value in memory, or we could put it into a register. What are the advantages and disadvantages of each approach? So if we put it in a register, we use it with another register, so that's a downside. But the upside is that it's in a register, right? And registers are faster to access than memory, right? The downside of leaving it in memory is we have to go to memory every single time we want to do this comparison, which is going to be slower than if we had it in a register. So what do you want to do? Do you want to put it into a register, or do you want to leave it in memory? Register. Memory. Register seems to win out, so who do you want to be num rows? What? So sure, you can pick EBX, but if you choose to use EBX, what are you going to have to do? What? Well, you have to save its value, right? And then make sure to restore it at the end, right? So let's say we want EBX to be num rows. That's perfectly fine. And it'll give us a good practice using these registers. But in general, right, you'd want to use A, C, and D up first before you go and start using the other ones you have to save, right? Because it's going to be a little bit more work to get them set up.
Even though A is going to be your forgotten, you could use it in the meantime as long as like the variable you're using isn't that important at the end when you override it with the return value.
So here's so you're correct, right? We could use EAX for whatever we wanted and then just at the end make sure that it got set to the return value, right? And pretty much no variable is going to be important at the end except the return value, right? So if we wanted to, that'd be fine. But so what we could do over here is we could do one more EQU if we wanted to. So you could do like dot EQU, and this one might be like old EBX, and it's going to be -4 times word size past percent EBP. But the thing to be careful about here is, remember, these EQUs do not make any space, right? If we want to make more space, make space for locals and saved reg, right? If we want to make sure that we save them, right, this is the thing that actually makes the space. So don't forget to change that, right? So now I've made more space so that we have space for our old EBX value to be saved at, right? So now how can I save the old EBX value? Move EBX to you could, but I'm just making it so it has a more uniform interface. So yes, if we wanted to, we could just do push EBX and that would have the same effect without the subtraction. But I'm doing it this way right now, and totally it could be just replaced if you didn't subtract and you pushed, you'd be fine. But let's say we're doing it this way, what we put here. Yeah, old EBX, percent EBP, right? You just keep following that pattern, right? Because we've already established where these locations are going to be at. So great, we've saved old EBX, right? And if EBX is going to be num rows, we might also have something like up here. Move out num rows past percent EBP to percent EBX. This is EBX is equal to num rows. Right, so EBX is num rows. So now how do we do this line down here? Comp L. Yeah, that's I minus num rows. And then outer for n, yeah. And then at the bottom, we need to make sure that we do our plus plus I. So plus plus I, that's going to be equal, right, for ECX, and then go back and do the next iteration. So jump to outer for start. Any questions about the translation of that line of code? Oops, not here. Oh. Oh wait, no. Oops, got confused. No semicolon there. And then these guys should all be indented, so I stopped getting confused. And this should be not I, but J. Oops, I copied the wrong one. That's why I got the wrong thing. Oh, we have to do this line first. So, how do we translate this line of code? Yeah.
What did it mean when you did call malloc like earlier?
I called malloc. Runs malloc.
Where's malloc?
It's in the C standard libraries. Again, we're not writing malloc. We're calling the C malloc function. Right? Remember, malloc creates space dynamically. So we're just calling the function. Yeah, we did. We pushed them, right, onto the stack. Line 53?
So malloc takes the stack arguments.
So again, according to the GCC C calling conventions, how do functions accept their arguments? On the stack, right? And they're pushed in reverse order of appearance. There's only one argument, so we push the one thing and then called the function. Right? So the same rules that we follow right now in writing our code are the same rules that the C code, right, is going to follow when you call it. So we're all following the same rules now. So that's why we can call each other. Yeah.
When you do this, you write it in a .s file or in a .file?
Well, this is a .s file, right? Assembly.
Do you need to ever download or like load malloc at the top, or how does it?
So the linker takes care of the linking about making sure the symbols are resolved, which is now like when you compile your code, you're going to compile with GCC, including the assembly files, instead of using like the AS and the LD. And then GCC will handle that for you.
So you can use any C function?
Yeah. But again, like switching to using print statements is going to be like a pain in the butt. If you're like, oh great, I can finally like, do print debugging again, right? Because to do the print statement, you have to push all of the arguments to print in the correct order, and then call printf, and hopefully you didn't screw that up, right? Versus again, just the debugger, you can just look at things. And hopefully you guys have been, or I guess ask, have you guys been like realizing how much more valuable the debugger is than before this class? It's become a much more useful tool for you to help you solve problems, hopefully, because it's a really, really useful tool because you can see what's actually happening, right? And when things break, you can ask the debugger to display what is actually going on, right? If I segfault on this line where I'm accessing memory, I can pin out like what's this register or that register that's involved with it and see like which one has the weird value, and then figure out then how did they get the weird value. And again, as you get more and more practice using the debugger, the better and better you'll get. Yeah.
What's the difference between GCC and G++? Because I've always used G++.
It's probably how they translate the C code into assembly is a bit different. We will show you some G++ code in a little bit, but the G++ compiler does something called name mangling, which will modify the names of the labels based on the parameters that the function receives. And so it will no longer just be your function name. It's like your function name concatenated with a whole bunch of weird stuff. So it will just make it like a lot harder for us to actually integrate into the assembly code, or integrate our assembly code in the C code if we were using G++ over GCC. Okay, so we have to translate this line of code. What do we do? Well, yeah. So we need to get num calls times size of int into a register. How do we do that? Right? Where's num calls at? right? It's going to be num calls past ABP because we set it up at the beginning. I don't have to keep thinking, right? So when you're trying to grab an argument from the stack here in class, it's just the name of the variable because we made the label for it, %EBP. That's always going to get it for you. So we can move out num calls past %EBP to what register? What? So sure, you can use EDX. It's currently not in use, right? We still don't have, we haven't used A or D, right, in terms of what's there. So this will be like EDX is equal to num calls. Now how can I multiply it by the size of an integer? Yeah, we can just do a shift left by 2 because an integer is 4 bytes big, so we want to multiply by 4. So shift left by 2 %EDX. This will make EDX be equal to this expression. So great, now we have the argument that we want to pass to malloc. How do we pass it to malloc? Push it. So push %EDX, and then how do we call malloc? Call malloc. Now, there's something we have to be slightly worried about at this point in time, right? Something just happened because of the rules, right? We called this function malloc. What assumptions does this function make? The return value is going to be an EAX, right? Arguments will be passed on the stack, right? And if you were using EAX, ECX, or EDX, you cared about them, you will have saved those values. So do we have anything in A, C, or D that we care about? What? ECX has I, right? So if we do this function call, ECX might be overwritten, right? Because again, it's following those same rules. Just like we overwrote ECX, it's just going to overwrite ECX if it decides to use it. So since we know this is going to happen, what should we do with what we have in ECX? Save it, right? So right before we do the call, we might do something like depends on how you want to do this. So you might say something like save numRows, not numRows, save I, right? So move L %ECX, right, to I past %EBP, right? We saved it, right? We put it out into memory. We now do our function call. Add L $1 times word size 2% ESP. Clear the arg. Move out I past %EBP back into EDX. Restore ECX. Restore ECX back to I. And then how can we do this last part? Remember, C was declared as integer ***. What? Do we have C in a variable? Well, we don't have C in a register, but we do have C in a variable. It's C past %EBP. Right? We did that back here. So right, previously EAX had C past EBP, but no longer because it got overwritten, right, by the function call that we just did to malloc. Right? But that's fine because we already made sure to save it. So, how do I do this? Of course, right? You're accessing memory, so you are going to be using the advanced indexing mode. Okay, move out EAX to this. Are we happy with this? Is everyone else happy? EAX is the return value from the function call, right? So it's whatever malloc returned. So right now, after we do call malloc, EAX has the result of the function call, right? Because return values are going to be placed in EAX. So you just did one of the things that I told you on Tuesday not to do. Right? I don't remember if they might have been in some other file, I think, where we said not to do them, but you did exactly one of those things. Right? So this does not do C at I is equal to the return value of the malloc call. Right? You got the return value of the malloc call correct, but it's not placed in the correct location. What does this line of C code actually translate, or this line of assembly code actually translate back to C code to? So EBP plus C is equal to what? Yes. I can agree with that.
Or can I please scroll up to like C is the last one stack?
So C is negative 12, and negative 12 plus EBP, I agree, is a number, but it's a number that represents what? The address of? The address of C, right? So we know that C plus EBP, right? That's equal to the address of C, right? So we know that this part over here is going to then add like I to it, right? So this is equivalent to like the address of C, that's ECX times word size is I. And then we take this entire expression and we dereference it. So this is going to be equivalent to the address of C at I. So get C's address and then go I past it. But over here, if we look at how this piece of code is translated up here, this is star C plus I. So is star C plus I the same thing as star ampersand C plus I? No, they're not. They're two different things, right? But again, it's a very, very easy mistake to make, right? Which I said, that's why I said don't do it yesterday. But it's okay. It's good to see it again. So how can we do it the correct way? Right? So first we have to get C into a register. How can we get C into a register? Move L, C past EBP. Again, right now we have both EAX and EDX. Or no, EDX is the only one that's free right now. So we're going to probably put it into EDX. Because EAX has the return result. Right? This is EDX is equal to C. And then how does this line of code change? And now we did it the right way. Right? Because EDX is C, right? C plus I, entire thing dereferenced, which is what we wanted. C plus I dereferenced. Any questions? Yeah.
For like convention's sake, should we do it this way all the time to try to access things this way? Like move, so like move C into a register and then do it to avoid mistake.
Basically, like with what I have right now, there is no other way of doing this, right? It's not just convention. There's no way of trying to that will allow you to write the equivalent expression the way that we started out with, right? You're going to have to get C first to then be able to go I past C. There's no way of shortcutting that. Yeah.
When you say C plus I, is that like the value that's stored in C and then add I to it?
Yes.
Okay.
So if the value at C was like the address, like if C held the address 100 and then I was 5, we basically get like 100 plus 5 times 4 if we want to go into bytes, so 120. Anything else?
So what's stored in C?
What did we put in C, right? Previously we put into C at that location in memory, right? We put whatever malloc gave us back before when we first called it. So I don't know exactly what the value is in C. It's just whatever malloc gave me. I mean, I don't. We can make up an example number, right? We could say that malloc gave me back 1,000, so then C has 1,000 in it. But if we actually go run it, I don't know what's going to give me. Any other questions? Okay. Now, here we go. How do we do this?
Yeah, I can't remember what was C.
Two matrices,
But like what's inside it?
numbers.
Get there.
What?
How did they get there?
Well, I mean, it's like asking like when you call a function, right? Someone's going to make sure they made the matrices first and then called your function with some numbers in it, right? So maybe someone did like 1, 2, 3, 4, 10, 20, 30, 40, right? Well, I mean, like, think about if you wrote some function that found the width, like the area of a rectangle, right? Accepts the length and the width. Does your function ever control what the length and the width are? Would it make sense trying to set them to something?
Well, I guess you set them in the .s file or you set them.
They're going to be done in the C file. So back over here in main.c, what we'll do is we'll read the command line files as to where the matrices are stored at. We'll read them in from their files, we'll add them, then we'll print them. But the values are going to be passed from the C code. But like normally that kind of question, like it doesn't matter where they come from, right? It wouldn't matter if they came from C code or C++ code or assembly code or however they got there, right? Because we're saying if you want to pass me these values, they're going to be passed on the stack. So whoever calls me, right, better make sure those values are on the stack if they want me to work correctly.
I just meant if you do it like in a output.s file or.
I'm not going to, right? But like even like if I did put some labels up there in the data section, they would not matter because that's global memory for something else, right? When I call my function, the arguments have to be passed on the stack. So I would never refer to it in the first place, even if you put things in the data section. Right? And for like your next homework assignment, you're not allowed to use the data section. You've got to use the stack. Any other questions? Okay, this line of code. How do we translate it? Currently, registers that we have in use are EDX and EAX, I guess, are both in use, sort of. Though EAX currently has C at I, right? So after we do this, EAX is equal to essentially whatever C at I is, more or less. Maybe we should do like about equal. They had the same value after we do these lines of code down over here, right? And EDX is equal to C. So you don't necessarily need C anymore. You can be happy without that because later on, if we look at our C code, we're going to need to do something CI at J. And if we already have CI, do we need J or do we need C? No, right? So we can free up EAX, or not EAX, we can free up EDX if we want to at this point in time. And then we also can still use in the future ESI, EDI, and then we're out of registers. So what register do you want to pick for J? What? EAX? EDX, sure. So we might say up here that EDX will be J. So again, move L $0 2% EDX, right? That's J is equal to 0. Inner for start, inner for end. So let's say this time we decide to leave num calls in memory. Probably not the best idea, but let's just do it for right now. What's this line of code going to look like? So, right, going to do a comp L with, well, who's J? Well, that's EDX. And how can we get num calls? Num calls past VP, right? Jump if greater than or equal to inner for end. Yeah, got that backwards. Good catch. And then now we're down here. So incl percent. Wait. Yeah, EDX. And then jump to inner for start. So fantastic. We translated this line of code. We just have 2 left. Right? And then we can maybe write some recursive code. Right? You guys have done this line of code before. How do we do it now? Right? The first thing would probably be to rewrite this expression without the square brackets. So without square brackets, this is, again, given they're declared like this up top, right? This is going to be something like, C plus I, plus, I always have to like do it going like backwards, star, parenthesis, star, right? Is equal to A and B. So how could we break this problem down? Yeah, you did, right? So it shouldn't be hard. So I don't know why, I'm not sure why you guys are all so quiet. Because we have done this before, right? Right? Let's say we probably want to get Aij somewhere, right? So how are we going to get Aij? Where do you want to put that into? Currently, the registers that are available, but we'd have to make free, would be ESI and EDI. Because we've used A, B, C, and D. Sure. So let's say we wanted to use ESI. So then back here, you could do something like save old ESI. And then here we could do push %ESI. But then down here, I'm going to make, again, another EQU to be old ESI just for later on. And it'll be -5. Okay, so great. ESI is available for you to use now. So what do you want to put into ESI? I is in ECX. So I is in ECX. So we're trying to get ESI equal to this. So move L. What's the first part? What do we got to get into ESI to begin with? Again, break the expression down. What do you have to get first in order to compute this entire thing? Right? We have to get A, right? So how can we get A into ESI? ABP, right? Again, it's really nice not to have to keep remembering exactly where those things are at. But again, if you had been using ESP, you might have had to keep updating these things. So this is ESI is equal to A. Then what do you want to make ESI equal to? Yeah. So move L. What to ESI? Okay. Now, great. We got that now. What do you want to do next? So same thing, but we probably want to get it into some other register maybe. At least partially we're going to have to, because we can't do summation until we get the value. So we probably need another register. We probably need EDI. Right? And again, it's pretty normal to like run out of registers. You only have a small amount. So if we wanted to save old EDI, push %EDI, and then make one more little label over here. So here we want to make EDI equal to, B at ij maybe, or at least B at I. So how can we make EDI equal to B? How can we do this? Move out EBP to EDI, and then we can do addl %EDI %ECX word size to maybe say %ESI, and now this is going to make A, or ESI is going to be equal to our summation. Where? This one?
The one above.
Oh, yeah, afterwards. I'm like, all the commas are there. So great. So we've saved it. Now we need to move the value there. So move L, ESI to, well, C at I is in EAX. But it's C at I is already in EAX. Oops, I messed up this one. It should be EDX. So it should be %DX word size. C at ij is equal to A at ij plus B at ij. Yay. Any questions? Yeah.
So after you move from EI to I, what should the same step as AIG?
So like, why is this one an add L instead of a move L?
Yeah.
So like, what I could do is I could have moved into EDI, BIJ, and then done on the next instruction, add L, like EDI to ESI. But that requires me to write one more instruction. And I'm lazy.
So you combine two steps.
Yeah, combine 2 steps. Okay. So great, we finished translating this line of code. Now we kind of just have to make this happen. How can we make that happen? Where do we put return values at? So we're gonna have to move something into EAX. What do we want to put into EAX? All right, so this will set the return value. And now we need to do the epilogue. Right, the epilogue undoes the prologue, right? So we have all those registers that we saved. We need to now, at least ESI, EDI, and EBX. We're gonna have to restore those. And you could do pop, 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 3 pops, right? Doing the 3 pops, though, you have to make sure that you did them in the correct order. Given that we essentially pushed EBX, ESI, and EDI, what order do we have to pop them in? EDI, ESI, EBX. We have to do pop ESI, pop EDI, or pop EDI, pop ESI, pop EBX. Or again, since we have these labels, we can just do the movements, and we don't have to think so much anymore about how to do it correctly. Which is kind of why I prefer having these little EQUs up here instead of having to remember everything that's supposed to happen. So first step would be to restore saved regs. So we'd have something like move L %EBX to old EBX past EBP. Move L ESI to, nope, that's the wrong direction, isn't it? Move old EBP, old EBX back to EBX. Move old ESI back to ESI. And then move old EDI back to EDI. Clear locals. Move L %EBP to ESP. Restore stack frame. I guess all of these should be indented 1 level, so let's know they're part of the epilogue. Pop %EBP. Right? These are all the instructions that I gave you last time for doing the epilogue. And now, since we're all done, how do we go back? Right. And we're done. Any questions? We'll definitely do some more examples over the coming days. One thing to kind of think about is there is some optimization that we could do over here in the assembly code. Notice that we keep doing A at I, B at I during each of the inner iterations. We keep accessing them. But in our inner iterations, will A at I and B at I be changing? No, so if we wanted to optimize, we could compute A at I and B at I outside of the inner for loop. And then you can just do AIJ, BIJ inside the inner for loop, and that would speed things up a little bit because we'd be doing fewer memory accesses. So that's one way to think about optimizing. If things remain constant in a loop, move them outside the loop so you don't keep recomputing them. So let's see if this works. Or if we screwed up. Oh, I must have forgotten something in line 102. Line 102. Oh, that's because There was not supposed to be an equal there. So we compiled, and again, if you want to look at the make file, right, we're just running GCC, but one of the main things is we keep compiling with the M32, which does the 32-bit compilation. You will probably have to install multilib on your computers to be able to compile with that, because you guys are all running 64-bit machines. So make sure you do that. There will be instructions in the next homework on how to install that, but it's just one command over here in Ubuntu. And now let's see if we can make this run. So we'll do our executable, which we called, where is our executable? Mat add.out, there it is. And then we'll do mat a.txt, mat b.txt. Yay, we did it! It did addition. Right, so it's running that C and assembly code combined, but don't think about it as a C and assembly code combined. It's assembly code and assembly code combined together to make machine code. It's just who was the person that translated the C code into the assembly code, right? For doing the actual mat add function, we were the compiler that translated our C code over to assembly code. Whereas the main file, it was translated to assembly code by the compiler, right? But we both produced assembly code at the end of the day. So it always ends up being assembly code calling other assembly code. It's never C calling assembly code. Or assembly code calling C. It's assembly and assembly, because that's what you end up with at the end of the day. Any questions before we do some examples? Yeah?
You don't have like a makefile name? Do you have to like run all of those like lines one by one?
If I didn't want to, so you could do it with a single line. You just list all of the source files on a single line. So like gcc-m32-g, and you know, turn all the warnings and stuff, and then you would do like main.c mat-add.s. So you list all the source files. The point of the make file, or if you were using like a CMake file, is to kind of like expedite the compilation process, because if you only change one file, you don't want to have to change the other, right? In terms of like the recompilation, because it can take a lot of time if you have to recompile your 20, 50,000 line, 100,000 line project, right? If you only changed one line in one file, right? You'd only want to, if hopefully you'd only want to have to recompile that one file and then link everything together, which is what the make file helps with. So let's do some recursive functions, because everybody loves recursion. Let's see. So we'll start with everybody's favorite problem, which is the Fibonacci. So first question, right, is you guys know all how to write the Fibonacci, right? I'm assuming you've all seen Fibonacci in like C or Python or some other language before, because it's what you always teach recursion with, right? If n is 0 or 1, return 1. Otherwise, return Fibonacci of n minus 1 plus the Fibonacci of n minus 2. I think this is on the wrong visualizer. Okay, so here we have our Fibonacci code. What's the first thing that we should do? Right, we're writing a function, so we're doing a C-style function. So what's at the beginning of every C-style function? The prologue, right? So we should do the prologue, right? So the first step of the prologue is to do what? Push EBP, move L %ESP to %EBP, right? And then it's make space for any locals that we have to do, right? Which I don't know if we have any locals to begin with, but if we do have locals, we'll make space for them, right? After we do this, what's the stack look like? So here's EBP, right? It's pointing to old EBP. And what's going to be above EBP? You know, I got +1. The return address, right? And then above that, your argument, right? So at plus 2, you're going to have n, right? So if we do our EQU down here, dot EQU, right, we can do n as being 2 times the word size past percent EBP. And then later on, yeah, we're going to have to do the epilogue somewhere down below, right? So don't forget to do that. But great, now that we've done our prologue, step numero uno. How do we translate this line of code? For? Sure, right? So we could have, fib if, end, fib if, or maybe, fib else is also where this kind of starts. So sure, we have our label. Sure, move L, n past EBP. What register do you want to put it in? Sure, ECX. So ECX is equal to n. Then comp L with ECX. Okay. Jump if equal to jump if not equal to so jump if not equal to, right? We could do so if it's not equal to, we could sure. I'm happy with that one. Right? So we could have like if body or something like down here. So you could do something like jump if equal to the if body, so sure. And if we fail, right, if it's not equal, what should you do? Comp L $1 with ECX, and then not equal to the fib else. Fantastic. Right, because if we fail, right, we know that we have to go into the else statement. So we're now over here in our if body. So what do we have to do? So move L $1 into, and then down over here, I'm going to turn this into a body. So we'll set the return value, and then we will jump the epilogue. So great, now we go run the epilogue, right? We have to clean up. Otherwise, right, we're going to go in the else statement, and you have to do this. Sure, you could. Which ones do you want to use? Currently, the only register that we're kind of using is ECX. So sure. So what do we want to put into EDX? Do you want to put n-1 or n-2 there? Sure, n-1. So how am I going to get Fibonacci of n-1 into how can we call Fibonacci with n-1? And get that result into EDX. But we want right now we have to get n-1, right? Right. So sure, we could do like decal ECX, right? That's ECX is now equal to n-1, and then push %ECX, then call fib. Okay, great. We've now called it the first time, and our return result is going to end up being in. So great. EAX is now has fib of n-1 in it. So what do I need to do now? Say it again. Sure. Where do you want to put the EAX at? I agree. You have to store it. Where do you want to store it at? Sure. Which one? So currently, like the only register that actually has something in it right now is which registers? Which registers have values in them currently? Does ECX have something in it? Maybe. Right? And then do any other registers have values besides ECX? Well, there's EAX, right? EAX has a value because we just called the function. Right? So C and A. So which one do you want to use? So sure. So you can then say like move L percent EAX to percent EDX, right? Save the return value. Or save, just like, probably a better way of saying this is EDX is equal to fib of n-2. Now what do you want to do? Yeah, sure, equal percent ECX. Push percent ECX. Call fib. Okay. Then what? Maybe like add a percent EDX to percent EAX. It has the sum. Right. So great, we're done with the else statement, and we now need to go do the epilogue. So what's the epilogue? Well, we didn't have any locals or arguments, so nothing that no save registers, so we don't need to restore anything. So do we move L percent EBP to percent ESP, pop percent EBP, and then rec. Any questions before we go and try this out? See if it works. How it did it again?
Yeah.
You called the function, right? Just like we did over here in the C code. We called the function, right? But with n-1 and n-2 instead of it with, the current value. So if we started with n was 4, right? Then we're going to call a function again with n is 3, and then n is 2, and then n is 1, right? So the function's being invoked multiple times. Anything else before we go and try running this? So I think this wants it on the command line. Yeah. So let's try doing this. So GCC -G-M32 main.c fib.s. Oops, line 26 apparently I have an error. Oops, yeah, an extra comma there. So now we can try running our executable, which is a.out. Let's say we pass it the Fibonacci of 0. We got the right answer. Fibonacci of 1, got the right answer. Fibonacci of 2, got the right answer. Fibonacci of 3. So what should we do, given that our code's not working? He's the debugger, right? We shouldn't just spend our time looking at it harder because, right, you guys all thought you wrote the right code. You know, maybe we're going to have to look at things a little bit harder because we can't see anything, actually, because DDD is tiny. So we'll break over here at fib, and we'll run our code. And we got a segmentation fault before we even got there. Oops, because I forgot to pass in the value. So run with 3. Right, that's where we broke last time. So great, we're now here, and so we might want to display some values. What would be useful information to know right now? Probably like what n is, right? So here's the trick for doing that. So we can say p, and then we're going to say integer pointer, $EBP, and going to need more parentheses because life is that way. So we're going to cast EBP to an integer pointer, and then how far past EBP is n going to be? Remember, it's 2 words. So here we should put 2 for index. Right? Right now it doesn't have the right value because we haven't done the prologue yet. But after the prologue is correct, and I guess I should probably change that to be a graph display so it shows up at the top. It has 3, which is what we expect. We know eventually that we segfault. So like if we continue, and we continue, and we continue, and we continue, and we continue. Notice right now, what's n? Up here. This is n. Okay. Oh, it's not. I don't know why. Sorry, I just thought it because it was like it was small, but I guess it's still hard to see. Is that better? It's -1. Well, should we ever get -1 if our code's correct? No, it's not. I'll let you guys know that you do still have some problems in your code, and all of them are related to the calling conventions. You broke them multiple times. Oops, not this. So you broke the calling conventions multiple times, right? Or at least in your assumptions. So again, what are our calling conventions? Return values placed in the AX. So if you're the caller, right, and you call a function and you have anything that you care about in A, C, or D, you must save those values before you make the function call, right? So did we follow that rule? No, right? Over here, right, when we called fib, right, on line 45, when we did line 47, what did we assume was in ECX? In line 47, what did we assume was still in ECX? n-1, right? But it's not guaranteed to have n-1. And given that we're actually calling ourselves, you can totally tell that you overwrote n-1 ECX because look, you overwrite ECX on your function call. Did you save it? No, but you shouldn't have had to save it up here because you're following the calling conventions. But now when you go to call another function, it could be yourself, you got to make sure that you follow them. So ECX, EDX, and EAX will all be overwritten, or you should at least assume they'll be overwritten when you do a function call. So after our call is complete, we no longer have n-1 in ECX. So how can I fix that? Yeah, so sure. Move L, n pass %EBP to %ECX. Sub L, $2 from %ECX, and then we can push it. ECX is equal to n again. ECX is equal to n minus 2. So that was the first time you broke the calling convention. There's the second time you broke it too. Do you know what it is? But n was never in a register, right? N was in memory. Right? It's on the stack. Does that make sense? N is on the stack.
Oh, it is ECS. So then, why do we use, if they're gonna get overridden, why do we not use like EDI?
Well, if you wanted to use like ESI and EDI, you totally could, but you have to make sure that you save them first at the beginning of your function. Right? Because the function that called you assumes you will not overwrite those methods, or not overwrite those registers, I mean. Right? So you're going to have to save it sometime or later, whether it's at the beginning or in the middle. Okay? Can you see the other time you broke it? I'll give you a hint. It's on line 51. Okay, this is line 51 right here. Sorry. So this line. You also broke the conventions again.
So we do not have EDX.
Yeah, EDX got overwritten, right? Because you made a function call right here. Right? So EDX got overwritten. Because again, you can't assume that, like when you call a function, assume those three registers, A, C, and D, will be overwritten. And since you can assume that those three will be overwritten, it's your job as the caller to save those values somewhere else. So instead of saving our return value from n minus 1 here, where should we save it instead of EDX? What are our options? Will any register work? No, what registers would work? ESI would work, or EDI, or EBX, right? The other ones that aren't A, C, and D. Or what's the other option besides putting in a register? Store it in memory, right? Which one do you want to do? Store it in a register or store it in memory? I mean, again, there's no right or wrong answer here. You just got to pick one. Sure, memory. So if we're going to put it in memory, how do we do that? No data section. And this would actually break if you did do the data section, because if we make a variable up here, right? Say like we had like dot data and we had something like, n minus 1, right? And we had dot long, right? And we tried to save it out here. This wouldn't work. Why? No, it doesn't have to do with where they're located at. It gets overwritten every single time, right? When you make something in the data section, right, it's in global memory, how many times do you create this variable? It's once, right? It gets created a single time. Now, how many n's are there going to be? Or like n minus 1s? We don't know, but we can safely say that there's probably going to be at least more than 1. But we need to be able to save all of them, because every time this function gets called, it gets a new n, and a new n, and a new n, and a new n minus 1. Right? And if we, this function ends up being called 10 times, then we have 10 n minus 1s, but we only have space for one of them. Right? So we could not make space in the data section. It wouldn't work. Right? But we could make space, not in the data section, but in, or on the stack. Right? So we could make space on the stack. So how can we make space on the stack for our variable? Right? So what do we do here? How can we make space for the locals? right? We want to make space on the stack. How do we make space? Sub L. And how much space do we need? How many things? 1, right? Times word size from ESP. And then down here, we can have a new .eq, n minus 1. That's at -1 times word size past percent EBP. Remember, so one kind of interesting to note is that all arguments are at positive offsets past EBP, and all local variables are negative offsets past EBP if you're using the stack frame pointer. So now, what can we do to save the value? What's this line change to?
Wait, did you please write n minus 1 or n underscore?
You can't literally write n minus 1, but n underscore 1 means n minus 1 in this context. So what do we put here? Right? So save fib of n minus 1. And this line of code now becomes, and n minus 1 past percent EBP. And we can try this again. Oops. TD stop. Now let's see if I screwed up. Seems to be working.
What does it mean if you put $sign in front of something on the stack?
What does it mean if you put $sign in front of something on the stack?
Like $sign C.
So like if we go back to our code and we wrote $sign, go back to our code, and we wrote like something like $sign n.
Like $sign and past. Like that whole thing.
You can't write that. But the intent is what I'm assuming that you're trying to do is get the address of
On the stack, yeah.
something on the stack. So that brings us into our next subject, which is, good job, there's an instruction called legal, which is load effective address long. So come back over here. So here's your new instruction. It's leal. And the format of this instruction is it's leal DOIS to some destination. Actually, the destination has to be a register here. And the effect of this instruction is register is equal to D plus O plus I times S. Now, how is this different from move? Right? So how does leal, DOIS, register different from movel, DOIS, register? Yes, so if we do the move, we dereference it. If you use leal, do not dereference. So that's how you can compute the address of something, right? You just add to it to get the values. Because we know that the address of something like n is its n, whatever that thing is, like 8 plus EBP. So we want to add 8 plus EBP. If you literally do like move L EBP to like EAX, add L8 to EAX, great, you have it. Or again, if you want to use a little bit more compact form, you can use leal. And you can basically treat it like the memory addresses you've been working with so far, but it will not actually do the dereference. So that's how you can do constants, or get addresses, or do like pointer arithmetic too, as well. Any other questions? Okay, I don't think we really have time for more examples, but next week we should wrap up the assembly code. Tuesday we should be done with like the stack stuff, and then Thursday we should be done with the inline stuff. And then we'll go on to the rest of the class, which is just like how does the operating system do things. like the interaction between the hardware and the software. I will see you either in office hours or I will see you next week.
Can I ask a question about this?
Yeah, 1 second.